Okay, now I'm recording. Okay, so this is the Math 2460 Zoom meeting. Students have just indicated they're okay with last week's stuff. Do you want a little introduction to this week's stuff?
Yeah, that sounds good.
Okay. If you think the formulas have been bad so far, you ain't seen nothing yet. Wait till you see the formulas in these next two sections. Just brief explanation of 7.3. They call it the shell method. All right. To understand what they're doing or why they're doing it, you got to sort of see the flaw in section 7.2. Or at least where they could, math is all about trying to perfect things or going, I don't want to do it that way. I want to do it another way. All right. If in 7.2, if you remember, if you went around the x-axis, you had f of x and you had integral dx. You had dx integrals. And this is what we like. Life is beautiful. But if you went around the y-axis, you had functions of y and you had integral dy, which if they really simplified things, they worked. But like I say, math is full of people who go, I don't like functions of y. I want to keep functions of x, which is what you're used to. They pass vertical line tests, but still keep dx integrals. So someone came along and said, I hate functions of y. Functions of y. And there are some you want to do and you can't really get functions of y. I want to keep functions of x but still go around the y-axis. I know since last week you've laid awake nights going, gee, how can I keep functions of x but still go around the y-axis? So I don't have to convert to functions of y and use these darn non-functions that don't pass vertical line tests. Well, I'm here to satisfy your wildest dreams. So they came up with a shell method. I'll try to keep it as short and sweet as I can. The shell method keeps f of x, but goes around the y-axis. Real quick derivation of where they're getting it. Same diagram, and we'll do a top and a bottom to shorten it up. But I want to go around the y-axis. It's going to mirror over here. I'm going to need the difference of the two. We'll call the difference of the two h of x. F of x minus g of x. Now, what this is going to form, if you can kind of see it, is sort of a hollow cylinder. So I'm just going to go with cylinders. Imagine this being a hollow cylinder, like a toilet paper roll or a paper towel roll. We'll have the y-axis right up through the center, and we'll call this R inner, the inner radius, and R outer. You remember your formula for volume of a cylinder? It's pi r squared, which is the area of one end, and we'll call the height h, pi r squared h. If I'm going to do a hollow cylinder, well, I'll start with pi r outer squared h. But you see, that's the entire thing, including your hollow core. So I'm going to subtract off pi r inner squared h, which gets rid of that hollow core. And that leaves your sort of solid part of it. Have we lost anybody? The rest of this is just algebra. Is this good? Can I proceed?
Yeah.
Okay. Let's we'll factor the pi to the front and the h to the back. To front, h to back. Pi, r outer squared minus r inner squared, and factor the h at the back. There's reasons for this. This r outer squared minus r inner squared is a difference of squares. Y'all are probably used to, something like x squared minus 4 goes as x plus 2, x minus 2. This is the same thing. You take the square roots and add and subtract them. Last line on this page, we'll make it r outer add r inner, r outer subtract r inner, and keep the h at the back. Okay. This first term smells like average radius, but I don't quite have an average. You get an average if you add two things and divide by 2. So that creates an average. I can't just divide by 2 unless I fix it by multiplying by 2. So I divide by 2 here to create an average radius and multiply by 2. This is differential radius. Difference of the radius. Let me rewrite this stuff on the back, next page. This gives me 2 pi r outer plus r inner divided by 2, r outer subtract r inner, and the h of x. H on the back, I didn't put the of x on that line. But okay, without going back to that other diagram, just real quick, your radii are aligned with x. So I can literally call this x. It's your average radius. This differential radius, I can call dx. And if you remember, the h of x was the difference of f and g, f minus g, f of x minus g of x, in effect, the height of the region. Plugging all that in, 2 pi x dx f of x minus g of x. All this is multiplied. I'm just separating it out so you can see the pieces. You want to add up the pieces. Which means you take an integral. You can bring in the Riemann sums and everything. I'm going to write all that gibberish down. Take an integral. This is what you got to remember. 2 pi integral. Collect everything with x under the integral. The dx goes at the back, and you're running it from a to b. Just don't forget you're going around the y-axis. This is the formula, but this is called shell method. It looks completely different from 7-2. And what I'll do is I'll do a problem both ways, the old way from 7-2 and this new way, and try to show you, because they look completely different. They give you completely different integrals. It's amazing to me, anyway, that they give you the same answer. Whoever figured this stuff out is a complete freaking genius, in my opinion. Well, naturally, somebody came along and said, well, gee, you could probably go around the x-axis, and that would give you functions of y again. And you'd actually have 2 pi c to d, a y, f of y minus g of y, dy. That would go around the x-axis. All right, yes, you can use this kind of formula. The book has a little section of problems telling you to do it this way, but actually you don't need to do this. If you see a situation like this, go around the x-axis, that's a signal to go back to washers or discs from 7-2. You can use washers or discs from 7-2 instead of this. The whole idea is to try to stay with functions of x. If you're going around the x-axis, functions of x, that signals washers or discs from 7-2. If you're going around the y-axis, f of x around the y-axis signals shells in this way. Before I charge into any examples, any questions about this? This is the important formula to remember right there. Plug and chug right into that for 7-3. Are you ready for some homework examples?
Yep.
Okay. Flip to some homework. And they start off with the same standard kind of thing. Give you some graphs. And they're saying use the shell method to write and evaluate your integral. And they're going around the y-axis, and they're giving you functions of x here. I guess I'll just charge into the first one, number 3. It's a simple one, y equals x. Page 470. Number 3, y equals x. So in effect, in the horizontal 45-degree line, they're going up to 2. spin it around the y-axis, which means you get a mirror over here. Around the y-axis. So find and my screen froze. I was too busy drawing and not looking at the screen. Okay, maybe I'm back. Okay. Find volume when revolved around the y-axis by the shell method. Okay, shell method says 2 pi x f of x minus g of x dx. It's very similar to an area formula in 7.1. It's got the same term here that you'd have in an area formula. It just got this extra x and a front coefficient of 2 pi. Amazing how similar the formulas can be, even though they calculate completely different things. Well, your f of x up here, that's your y equals x, is just x. So it's the same logic. It's top minus bottom. So this is your f of x. Your g of x is 0 on this one. So it'd go 2 pi, 0 to 2, x times, well, your f of x is x again, so x for here. I'll complete it right in 0, dx. And you get a pretty simple integral out of this one, 2 pi, 0 to 2 of basically just x squared dx. I'll go ahead and punch this in and check the answer in the back. Math 9. I'll start with the 2 pi, then hit math 9, or you can put the 2 pi inside. 2 pi math 9 x squared comma x comma 0 comma 2 16.755. Show that. I don't know how helpful this is since y'all probably have the new interface. At least it shows the answer I got. Let's look it up, see if I'm an idiot. Probably am. Let's see. 7.3, number 3. Well, they're getting 16 pi over 3. Book. All right, if anybody wants to give us a drum roll. We like the drama. 5 by 3. Yep, there we are. If that gives anybody any confidence in this. I could do it the other way, but I don't want to confuse things. Further down the page, they set up situations where you have to do things both ways to show you. Set up the integral like with the washer method and with the shell method. It's amazing that they give you exactly the same answers. Anybody want to see a Another one, through problem 11, they're giving you this classic situation, function of x around the y-axis. 13, they're going around the x-axis. In fact, it's the same diagram, but he goes around the x-axis in 13. They tell you to use shells, but again, you don't have to be a slave to their method. This is what they're trying to tell you to do over above problem 7. Choose a method. Decide whether it's more convenient to use this method or shell method to find the volume. Explain your reasoning. They're telling you do not find the volume, but actually I go ahead and do it. The reasoning is keep functions of x, whether you're going around the y-axis or the x-axis. Anybody spot anything on the page you want to see? Since 13 is exactly the same region, let me go ahead and show you both methods, see the different integrals you get, and you can punch them both and see that you get the same thing. You want to see 13?
Sure.
13 is exactly the same region, but they're going around the x-axis. This is still off page 470. Exactly the same region, y equals x. I don't know why I drew a right triangle. You don't have to have a right triangle. I guess because I just get out of trigonometry. You don't have to have a right triangle there. But you're going up 0 to 2. Okay. Yeah, you don't have to have that. So let's, we're going around the x-axis. They tell you use shell method. All right, this is the way I don't really like, which I don't like. It's going to give you an integral dy. Full formula would be 2 pi integral c to d let's see, of y, f of y, minus g of y, dy. Now, you can twist this around and x equals y. And so you see this is your f of y here equals y. And you're still going up 0 to 2 here, but along y. 0 to 2 along y, 0 to 2 along x. So it's going to look very similar. You'll have a 2 pi integral from 0 to 2, but again, these are y numbers, not x numbers. Y, and your f of y equals y. Actually, no, be careful, because you got a horizontal. Actually, your f, you're going right minus left. So actually, this is your right, this is your left. So actually, your right is just 2, and your left is minus y, dy. Let me punch that out, and again, I'd really punch it in x. We'll get a number, and then I'll set it up the other way. You have 2 pi, math 9. I'm going to use x, parentheses 2 minus x. Because you can punch it in any letter you want. Comma x, comma 0, comma 2. Come up with 8.3775. What do you call what? I'll just use that. 8.3775. Okay. Here's the preferred way. use washers. 7.2 washers. That would give you pi, because this keeps function of x. Integral a to b, and you'd have f of x squared minus g of x dx. I'll redraw the diagram down here. So now your y equals x, that is your f of x, equals x again, keeping everything in terms of x. G is 0. So this is your f equals x. Your g is 0. You're still going from 0 to 2, but horizontally now. Integral from 0 to 2, you'd have x for f of x, and this goes in as squared minus 0 squared dx. In effect, integral from 0 to 2 of x squared dx. So this looks completely different from this. It's amazing they give you the same answer. Let me punch it, we'll see. In fact, if we don't get the same answer, I will go and get my dream job. Walmart greeter. I'm about to retire. Math 9. X squared, comma x, comma 0, comma 2. Looks completely different. In the normal classroom, I'd have everybody give us a drum roll because the drama should be very heightened here. Can you stand the drama? Is this going to work out the same? Doggone it does. It's amazing. 8.3775. I would ordinarily, this is what I miss about the regular classroom. I miss your oohs and ahs of amazement that these would actually, you doing completely different way would actually give you the same answer. I'm amazed, but I guess I'm pretty simple. Is anybody else out there amazed? Did this prove anything to anybody or only to me? Not getting much response. Your amazement must have, you must be so amazed you can't even speak.
Yep, so amazed.
I'm so amazed, yeah. Absolutely amazing. Okay, did anybody want to see any others further down the page? The bottom line is you really don't have to use the shell method around the x-axis since it goes to dy integrals. You really can set them up by 7-2. So you to try to drive that home, you want to see 15?
Sure.
Okay. So you go to 15, still page 470. And it's taken y equals 1 over x. They give you the graph of it, kind of dying curve, and they're starting it at 1 and going it to 2. And they're going around the x-axis. All right, the book says shell method. Or use, but I know I'm going to have an integral dy if I do that. I don't want that. So I am going to use washers. Really disc because it's solid, but I always call it washers. this will give me an integral dx. So I'm going to do it by pi integral a to b f of x g of x dx. This is your f of x. It's 1 over x. You can put it in as a square. Your g of x is 0. This is your f. This is your g, top over bottom. So I'm going to get pi integral 1 to 2, 1 over x quantity squared, 0 squared dx. I can go ahead and punch away on that. Pi, function integral, math 9, 1 divided by x squared, comma x, comma 1, comma 2. .57. That smells like pi over 2. Probably pi over 2. Look it up. 7.3, it was 15. 7.3, 15. Pi over 2. Oh, by the way, they actually write out the integrals you'd have to do to work this by the shell method. Look how it takes 2 separate integrals by the shell method, and you wind up with pi over 2. I can show you those 2 separate integrals if you want to see them, why you have to do it that way. But it just, I don't know, may add to the gibberish.
Like on the test, we wouldn't need to do that.
We don't check your method.
Okay.
On the test online, I'm going to have this written out, and you'll check through my work and see if I did it right or if I screwed it up.
I know you were saying that this test might be the one that's proctored. Is it not?
You know, I'm not really sure anymore. God, I've looked through that proctoring, and it, oh man, it's driving me nuts. You're supposed to give y'all a practice grade before a real test grade. So I'm actually supposed to do a quiz, one of these quizzes as a proctored, just to give you practice using it. And
That's weird.
yeah, so I don't, it may come later. I'm not quite sure anymore. I didn't get a whole lot done I was planning to do online over Labor Day because I've got a family life. I'm trying to make everybody happy. So I didn't get much schoolwork done as I planned on proctoring the stuff, and so I'm behind looking at that. But we'll definitely announce the proctored grade before we have it.
Solid.
Does anybody want to see the shell method done on this? Like you say, they wrote out the 2 integrals in the back of the book. You get to the same answer.
I'm personally fine without. I don't need it because
Okay.
I'm just gonna use this way.
Yeah. Are you ready for different lines? Because that's what they do by problem 23.
Yeah.
Okay. It's just a variation off last section. In fact, it's a little shorter. When you do shell method, maybe I should go to the next page. With different around different lines. I really don't have to spread out all 4 cases. When you do shell method around different lines, here is the main formula. And that went around the y-axis. All right, if you remember, x, this was the radius term. Remember, we had a region here. There was your f, that was your g. And x is the radius term out to it, the average radius out. This is what you modify. Can't spell what. What you modify around different lines. And it's the same system as last section. I'll show you why it's shorter. Try 23 is the first one they ask. 23 takes 2x minus x squared, y equals 0, around x equals 4. All right, we'll want a graph of that. Two x. Okay, clear off. Okay, so we want a graph. Do that off. 2x minus x squared. Good window. Yep. Graph. Okay, comes up through the origin. Looks like it goes down through 2. Just to make sure. X is 2. 2 times 2 is 4. Minus 2 squared is 4. Yeah, 0. So yeah, 2x intercepts are 0 and 2. So we're taking this around x equals 4. So 3, 4. X equals 4 is vertical. Same idea as your shell. So this would mirror over here. Functions of x around the y-axis was vertical. That said shell. Functions of x around a vertical. This is shell with integral dx. So you're going to get a dx integral around the y-axis, which is the basic method up here. Dx integral around the y-axis. You get dx integral around any vertical. Since the y-axis is vertical, it's the same thing around any other vertical. But here's the rub, okay? I write down pi, 2 pi, integral a to b, but I write in the word radius, f of x minus g of x dx. Again, this is around x equals 4. Okay, same idea as last section. You start here and go into here. Forward, it's called x. I'll call this, there's just one radius. There's not an outer and inner radius here. That x plus your radius has to total 4 for this case. This is 4. Your radius is just 4 minus x. And since this is an x and you got a dx integral, you're fine. There's no substitution to make. So that is how, on this example, that radius gets modified. This is still your f, your g is 0. It will go 2 pi, integral 0 to 2, 4 minus x. See, last section we had to substitute for that letter because the letters were switched. They're not switched this section. Your f is 2x minus x squared. Your g is 0 dx. Anybody want to see that punch to show you get the answer in the back? Or you think we're okay? We're approaching 45 minutes. Not hearing any response. Anybody want to see that?
I think we're good.
Think we're good?
Yeah.
Okay. That about finishes section 7.3. Oh, we got somebody raised their hand. An iPhone raised hand. Can you tell us? Can you talk to us? I have to click something to hear you.
I want to ask a really quick question.
Yeah, absolutely.
On the last one, dx, do we put 4 or no? Because x equal 4, right?
That is the axis you're going around. The 4 comes in here on the radius term.
Oh, I got it. I got it now.
The limits on the integral go where the functions are valid. They stay 0 to 2.
Yes.
Go 0 to 2.
I'm not the people who raise the hand. I think you can ask who asked to raise the hand.
Did somebody else raise their hand? Don't hear anybody.
Yeah, it looks like the hand was put down.
Okay. Well, there's still 7-4 for this week, but we're at 45 minutes, and I don't know how much you can absorb in one session. They're calculating arc length and surface area in 7-4. Is this enough for this time? And in the next Zoom meeting, we'll cover 7-4?
Sure.
That sounds great.
All right, sounds good. Anybody have anything else you want to say or ask before we end the meeting then? Okay, we'll end the meeting. I appreciate y'all coming out early on this morning. So we'll end the meeting and look for you again on a Zoom meeting Friday. We'll see you then.
All right. See you Friday.
Friday.